Your phone knows where you are. Right now, within a few meters, it knows your position on a planet with a circumference of 40,000 kilometers. You open an app, a blue dot appears, and you navigate to wherever you're going without thinking twice about it. Here's what you probably don't think about. That blue dot only appears in the right place because of Albert Einstein, because of theories he published in 1905 and 1915, because engineers building the GPS system decades later discovered they had no choice. If they ignored relativity, the system was wrong by 10 kilometers per day, not slightly off, completely useless for navigation. Relativity is not abstract. It is not academic. It is infrastructure. It runs in the background of the technology in your pocket, correcting for the curvature of space-time and the slowing of time continuously, right now. Let's understand how. GPS is a constellation of 31 operational satellites orbiting Earth at an altitude of about 20,200 kilometers. Each satellite carries atomic clocks, the most precise timekeeping devices ever built. And each satellite does one simple thing continuously. It broadcasts a radio signal containing its identity and the exact time according to its clock. That's it. That's the broadcast. I am satellite number 4, and the time is precisely this. Your phone receives that signal. It notes when the signal arrived. It knows when the signal was sent. The difference is the travel time. Multiply by the speed of light, roughly 300,000 kilometers per second, and you have the distance to that satellite. One satellite gives you a distance. You're somewhere on a sphere of that radius around the satellite. Two satellites give you the intersection of two spheres, a circle. Three satellites narrow it to 2 points, usually one of which is obviously wrong. 4 satellites, and this is the elegant part, 4 satellites let your phone solve for something extra, its own clock error. Your phone doesn't have an atomic clock. It has a quartz oscillator that drifts. The 4th satellite signal gives the system enough equations to solve simultaneously for 3 position coordinates and 1 clock offset. 4 unknowns, 4 equations, clean. The whole system is a timing system. Position is derived entirely from time, which means if the clocks are wrong, even by a tiny amount, your position is wrong by a proportional amount. And here's where physics enters, unavoidably. GPS requires timing accuracy to within about 20 to 30 nanoseconds to achieve meter-level position accuracy. 1 nanosecond of error equals 30 centimeters of position error, because that's how far light travels in 1 nanosecond. The relativistic effects on GPS satellite clocks amount to a combined drift of about 38 microseconds per day, 38,000 nanoseconds, against a tolerance of 20 to 30. Uncorrected, GPS position errors would accumulate at roughly 10 kilometers per day. Within minutes of operation, the system would be wrong enough to be dangerous. Within a day, it would be catastrophically wrong. This isn't a minor engineering footnote. It's the central physical challenge of the system. The engineers had to get the relativity right, or there was no GPS. 2 effects, both relativistic, working in opposite directions. The first is from special relativity, the one most people have heard of. Moving clocks run slow. GPS satellites orbit at roughly 14,000 kilometers per hour. That's fast by human standards. It's a tiny fraction of the speed of light, about 0.004%. But with atomic clocks precise to nanoseconds, even that tiny velocity matters. Special relativity says a clock moving relative to you ticks slower than a clock at rest relative to you. This is time dilation due to velocity. The faster the clock moves, the slower it ticks. At 14,000 kilometers per hour, the effect is small, but it's real and measurable. The result? Satellite clocks tick slower than ground clocks by about 7 microseconds per day, 7,000 nanoseconds, against a 20 nanosecond tolerance. This alone, uncorrected, would produce position errors of over 2 kilometers per day. That's the special relativistic effect. Now the general relativistic one, and this one is bigger and more counterintuitive. General relativity says gravity slows time. The deeper you are in a gravitational field, the stronger the gravity pulling at you, the slower your clock runs. At Earth's surface, you're sitting at the bottom of Earth's gravitational well. GPS satellites at 20,200 kilometers altitude are much farther from Earth's center. They experience weaker gravity. And weaker gravity means their clocks tick faster than clocks on the ground. Not slower, faster. Satellites are higher up, less gravitational influence. Their time runs faster relative to us. The effect? Satellite clocks gain approximately 45 microseconds per day due to gravitational time dilation. So now you have two effects. Velocity slows the satellite clocks by 7 microseconds per day. Reduced gravity speeds them up by 45 microseconds per day. The net: satellite clocks run fast by 38 microseconds per day. 38 microseconds every day, accumulating, building into position error at 10 kilometers per day if left uncorrected. Here's the remarkable engineering response. Before each GPS satellite is launched, its atomic clock is deliberately set to run at the wrong rate. Specifically, it's tuned to tick slightly slow, at a rate adjusted by about 4.464 parts in 10 billion. This fractional adjustment exactly compensates for the relativistic effects the satellite will experience once it's in orbit. On the ground, the satellite clock ticks measurably slow. In orbit, experiencing the combined effects of reduced gravity and orbital velocity, it ticks at exactly the right rate. The satellite is launched broken, deliberately, so that the laws of physics will fix it. This isn't a software correction uploaded after the fact. It's baked into the hardware. The clock's oscillating frequency is set before launch to account for physics that will only take effect 20,000 kilometers up, moving at 14,000 kilometers per hour. That is applied general relativity, manufactured, into a satellite, using an equation Einstein wrote in 1915. The atomic clocks themselves deserve a moment, because without them, none of the relativistic corrections matter. Atomic clocks work by counting the oscillations of atoms, cesium atoms typically, which oscillate at a frequency of exactly 9,192,631,770 cycles per second. This number isn't arbitrary. The second is now officially defined as exactly that many cesium oscillations, not by the rotation of Earth, not by any astronomical observation, by atomic physics. The stability of this frequency is extraordinary. GPS satellite clocks are accurate to about 1 part in 10 to the 12th power. They would drift by roughly 1 second over 30,000 years. This precision is what makes nanosecond-level timing possible. And nanosecond-level timing is what makes meter-level positioning possible. Atomic clocks and relativity are co-requirements. You need both. The clock precision to measure at nanosecond scales, the relativistic correction to keep those clocks synchronized across the system despite the very different physical environments of orbit versus ground. Either one without the other would fail. The relativistic corrections don't stop at time dilation. The GPS system has to account for several other physical effects. The Sagnac effect. Earth is rotating. By the time a GPS signal travels from satellite to receiver, the receiver has moved. Earth has rotated slightly beneath it. The signal path isn't through stationary space, it's through a rotating reference frame. The correction for this effect is derived from, yes, special relativity. The relativistic Doppler effect. The satellite is moving relative to the receiver, shifting the frequency of the signal. For high-precision GPS, the kind used in surveying, scientific measurement, and precise timing, this shift matters and must be corrected. Atmospheric delays. The ionosphere and troposphere slow and refract GPS signals. The ionospheric delay alone can introduce errors of meters to tens of meters. GPS receivers use models of atmospheric conditions updated with real data to correct for this. Multipath errors. In cities, GPS signals bounce off buildings before reaching your receiver. The reflected signal travels a longer path, arrives slightly late, and corrupts the distance calculation. This is one of the harder problems. It's why GPS is less accurate in urban canyons than in open sky. The GPS system is a stack of physical corrections, relativistic and classical, applied simultaneously, continuously, invisibly. Most users never think about any of it. It works because physicists and engineers thought about all of it in extraordinary detail. Here's the deeper thing, the thing that should land. GPS doesn't use relativity because engineers wanted to be clever. They had to because reality is relativistic, always, at every scale. We tend to think of relativity as something that matters only in extreme conditions, near black holes, at velocities approaching the speed of light, in exotic laboratory experiments. That's wrong. Relativity operates everywhere, at all speeds, at all gravitational potentials. The effects are just too small to notice without extremely precise instruments. The GPS satellite clocks made the effects visible. At 14,000 kilometers per hour orbital velocity and 20,200 kilometers altitude, the relativistic drifts are tiny, but large enough to overwhelm a system that needs nanosecond precision. So engineers were forced to confront what was always true. The flow of time is not uniform. It depends on velocity and gravity. It's different for a satellite than for a phone sitting on a table. Every clock you've ever used has been running at a relativistic rate, slightly different from every other clock at a different altitude or moving at a different speed. The clock on your wrist runs slightly faster than an identical clock in a basement. Your clock in an airplane runs slightly slower due to speed and slightly faster due to altitude. The net effect is a tiny gain, consistent with calculations and confirmed experimentally. We just normally lack the precision to notice. GPS didn't lack the precision. and so it couldn't pretend the effect wasn't real. Right now, orbiting Earth at 14,000 kilometers per hour, 20,200 kilometers overhead, are 31 satellites. Each one carries a clock that was deliberately set wrong on the ground, tuned to compensate for space-time curvature and time dilation it would experience in orbit. Each one broadcasting the time with nanosecond precision, each one making your navigation possible. The signal reaching your phone right now has been corrected for special relativistic time dilation, gravitational time dilation, the Sagnac effect of Earth's rotation, ionospheric delay, and your receiver's own clock error. All of it. In real time. Continuously. Einstein published the general theory of relativity in 1915. He never saw a transistor. He never imagined a smartphone. He was following his equations, the curvature of space-time, the relationship between gravity and the flow of time, to where they led. The equations didn't know they'd eventually run in a constellation of satellites. They just described reality. And reality, it turns out, is exactly what the equations said. Every time GPS works, and it works billions of times every day, it is a live, continuous, experimental confirmation of general relativity. Not in a physics laboratory, not in a peer-reviewed paper, in your pocket, on your commute. Every time you ask your phone where you are, and it answers correctly. Relativity isn't something that happens elsewhere, in extreme conditions, to other people. It happens here, right now, every single time you navigate.